So this is MCV 4U1 Unit 7, page 531, question 9a. So the question is, solve the system of equations using elementary operations, interpret results geometrically. So we have the three planes, x take away 2y plus z equals 3, 2x plus 3y take away z equals -9, and then 5x take away 3y plus 2z equals 0. So what are we trying to do here? We're trying to solve the system of equations. So the first thing that we want to do always is examine the normals of the planes to see if the normals are scalar multiples of each other, which means to see if the planes are parallel or not. And if they're not parallel, that means that they must intersect somewhere. So the normal of the first plane, I'm going to call that n1, is 1, -2, 1. The normal of the second plane, which we'll call n2, is 2, 3, -1. And then the normal of the third plane, which we're going to call vector n3, is 5, -3, 2. So if they're scalar multiples of each other, okay, we're going to first test to see if n1 and n2 are scalar multiples of each other. So to get from this number to this number, we're going to have to multiply this by 2. Okay, that works, I guess. -2, but -2 times 2 would be -4. But here we have a 3. So we know that n1 and n2 are not scalar multiples of each other. Now we're going to see if n2 and n3 are scalar multiples of each other. Well, we can look here at this middle coordinate, and 3, to get to -3, you have to multiply by -1. Okay, so let's try that here. 2 times -1 is -2, but here we have 5, so we know that n2 and n3 aren't scalar multiples of each other. Now we're going to examine to see if n1 and n3 are scalar multiples of each other. To get from 1 to 5, we'd have to multiply this by 5. Okay, -2 times 5, however, is -10, and here we have -3. So we know that n1 does not equal kn2, which does not equal kn3. So this means that they're not parallel. So the planes are not parallel. Therefore, they must intersect somewhere. So now we know that the three planes intersect somewhere, but where? Okay, well, to determine where they intersect, we have to first find the scalar, the triple product of the three normals to see if the planes are coplanar or not. So triple product, normal 1 crossed with normal 2 dotted with normal 3 is the triple product. So if the triple product is 0, that means that the planes are coplanar and they intersect at either a line or they form a triangular prism. But first we got to determine what the triple product is. So n1, like we said before, let me just write this out again. 1, -2, 1, normal 2, 2, 3, -1, and then normal 3, 5, -3, 2. Okay, and 1. So we have 1, -2, 1. Write this out twice. Then write normal 2, 2, 3, -1, 2, 3, -1. Dotted with n3, which is 5, -3, 2. Cross this out. Okay, so now we have -2 times -1, which is 2, and then 3 times 1, which is 3, but the negative of 3 is -3. 1 times 2 is 2, -1 times 1 is -1. The opposite of that is +1. And you have 1 times 3, which is 3, and 2 times -2, which is -4, but the opposite of that is +4. Dotted with 5, -3, 2. We're just going to simplify this. So we have -1, 2 plus 1 is 3, 3 plus 4, 7, dotted with 5, -3, 2. And then now we're going to do some simple dot product. -1 times 5 is 5, and this is a scalar. 5, -5 3 times negative 3 is negative 9. 7 times 2, 14. So now we have negative 14, because negative 5 subtract 9 is negative 14 plus 14, which equals 0. So the triple product of the three normals is 0. So now we know that the planes are coplanar. So they'll either intersect at a line, or they'll form a triangular prism and have three different lines of intersection.
So now we know that they intersect at a line or also form a triangular prism. So in order to determine whether or not they intersect on a line or form a triangular prism, we're going to use elementary operations to determine whether or not they intersect on a line or form the triangular prism. And if the solution is inconsistent, then we know they form a triangular prism. And if it is consistent, then they intersect at a line. In order to solve for this inconsistency, we need to eliminate a variable, in this case x, to determine whether or not they intersect at a line or form a triangular prism.
So now we have to test for consistency. So for this first new equation, we're going to be working with equation 1 and equation 2. So I need to eliminate x. I need to do a system of equations which I eliminate x. So what can I do? Well, I can multiply x by negative 2, or I can multiply the first equation by negative 2, so I get an x coefficient of negative 2, and then I can add this multiplied equation to equation 2, so that I'll end up with 0x in that equation. So basically I'm just eliminating for x. So what that looks like is negative 2 multiplied by equation 1 plus equation 2 will give us our fourth equation. So first I need to multiply negative 2, equation 1 by negative 2. So I have negative 2 multiplied by x, take away 2y plus z equals 3 multiplied by negative 2. And then that'll give me negative 2x plus 4y take away 2z equals negative 6. So this is our new equation 1. And then now what we're going to do is we're going to add equation 2. So equation 2 is 2x plus 3y take away z equals negative 9. So when we add these two together, we get our fourth equation, which is 0x plus 7y, negative 2, take away 1, negative 3z, equals negative 6, take away 9, negative 15. So that's our fourth equation. Now, for our fifth equation, let me just divide this here. For our fifth equation, we're going to be working with equations 1 and equation 3. So what can we do here? Well, we can take the first equation and multiply this by negative 5, so that when I add this new equation to equation 3, we'll have 0 as our coefficient for x. So what that looks like is negative 5 multiplied by equation 1 plus equation 3, and that should give us our fifth equation. Okay, so what that looks like is negative 5 multiplied by x take away 2y plus z equals negative 5 times 3. And our new equation 1 for this system of equations is negative 5x plus 10y take away 5z equals negative 15. So that's our new equation 1. And then now we're going to add equation 3 to it. And that is 5x take away 3y plus 2z equals 0. And we're adding, and that will give us a result of 0x. Should I use a different color? I'll use a different color for this. That'll give us 0x take plus 7y, negative 5 plus 2, negative 3, negative 3z equals negative 15. So we have our equation 4 and 5, and just from observation, we see that the solution is consistent. But just for the sake of this video, we're going to create our sixth and final equation, equation 6, by eliminating, let's say, variable y. So we see that they're even, so what we can do is just subtract the two equations from each other. So then let's just subtract that, and then we'll get equation 6, which 0 take away 0 is 0x. 7 take away 7, 0y. Negative 3 take away negative 3, which is negative 3 plus 3, which is 0z. And negative 15 take away negative 15, which is negative 15 plus 15, which is 0. So we have this final equation, and this means 0x plus 0y plus 0z equals 0. Well, they're all zeros. The coefficients to all the variables are 0, so that means x, y, and z can be anything. There's an unlimited amount of possibilities to give us 0. So then this means that we have to introduce a parameter because the planes will intersect at a line. So now we know that the three planes intersect at a line, so we have to introduce a parameter. So what I'm going to do is take my fourth equation, if you remember, 0x plus 7y take away 3z equals negative 15, and I'm going to let z equal s, a parameter, because from our sixth equation, we know that 0x plus 0y plus 0z equals 0, so z can be anything. So I'm going to let z equal the parameter s. And now I'm going to substitute s into the fourth equation to solve for y in terms of s. So I have 0x, I'm just going to ignore that and write 7y take away 3s equals negative 15. So I'm going to move the negative 3s to the other side. 7y equals negative 15 plus 3s. And then we're going to divide both sides by 7 to get y equals negative 15 over 7 plus 3s over 7. Okay, so we know z in terms of s, and we just found out what y is in terms of s, which was negative 15 over 7 plus 3 over 7s. Okay, now all we need to know now is we have to determine x in terms of s. So we can take our first equation, equation 1, x take away 2y plus z equals 3, and we can substitute the values of y and z into the equation to solve for x. So that's what we're going to do right now. We're going to solve for x. So x take away 2y, negative 15 over 7 plus 3 over 7s plus z, which is just s, equals 3. Okay, this is going to be a long process, but it's okay. So now we have x, negative 2 times negative 15 is 30. So plus 30 over 7, and then negative 2 times 3 is negative 6. Take away 6 over 7s plus s equals 3. Okay, so what I'm going to do, I see these fractions, but I don't like these fractions. So I'm going to change 3 into a number, a rational number with the denominator 7. So I know that 21 over 7 is the same as 3 because 21 divided by 7 is 3. So now what I want to do is I want to isolate for x. So I have x equals 21 over 7, take away 30 over 7, take away 6, oh, not take away, it'd be plus 6 over 7, because I'm moving to the other side, take away, 6 over 7s, take away 7, take away s, yeah, so that's x, and then 21 take away 30 is negative 9 over 7, and then you have 6 over 7s, take away, you can also write s here as 7 over 7s, and then 6 take away 7 is just negative 1 over s, 1 over 7s. So this is our new value of x right here. X equals negative 9 over 7 subtracted by 1 over 7s. Our values of x, y, and z in terms of the parameter s. So the solution to the system of equations is, we said x equals negative 9 over s, take away 1 over 7s, y equals negative 15 over 7 plus 3 over 7s, and then z equals s, and remember the parameter s belongs to all real numbers. So the solution to the system of equations in parametric form is this right here.